Hello, ladies and gentlemen. Today we're going to go ahead and start our Chapter 7 notes. So at the very top, please go ahead and write Chapter 7. Now, remember, during small groups is when we check our notes, and you are required to take all of our notes and have everything written down that I'm doing in our video for each chapter. So we're going to go ahead and start Chapter 7, which is all about exponential functions, which are like a geometric function that we learned last semester. And we're going to go ahead and take a look at exponential functions overview. And we're going to go ahead and look at exponential functions in a variety of ways. So we're going to go ahead and take a pen, and we're going to do kind of a squiggly line down the middle. And then kind of far up to the top, about a quarter of the way up, we're going to do a little squiggly line going across as well. Now, what is the definition of an exponential function? It is a function that has a variable in the exponent, hence the name. Okay, and we've gone ahead and we've taken a look at exponential functions throughout our geometric sequences, and we know that they fall into the equation like a geometric function as well. Y is equal to a times b to the x power. Now, our a in this equation is our 0. That, of course, is our y-intercept. It's where the equation crosses the y-axis. Our b is our multiplier. And we have a lot of information about multipliers. We had a set of notes, and we're going to have a review next class about multipliers because they're that important. But if we know that our b is greater than 1, then we know our sequence or our equation is getting bigger. And this is what we call exponential growth. However, if our multiplier is between 0 and 1, then we know it's getting smaller over time, and this is known as exponential decay. Okay, so we have a lot of information when we simply look at the equation itself. We know where it crosses the y-axis, and we know whether it's getting really, really big, really, really fast, or really, really small, really, really fast. So we're going to look at two examples, one decay and one growth, and we're going to look at it as a graph, an equation, and we're going to look at it as a table of values as well. So our first equation that we're going to be looking at is y is equal to 10 times 0.5 to the x power. Okay, so we're going to go ahead and make a graph. And we're going to basically go up to about 20, 5, 10, 15, 20. Okay. And then on the other axis, our x-axis, we're just going to go ahead and count by ones and go 5, -5. Okay, so go ahead and set up your axis like that. And we know because our multiplier is at 0.5, that's a number between 0 and 1, we know this is going to be an exponential decay. And we want to go ahead and take a look and see what that looks like. Now, the easiest way to do this is to make a table of values and then plot those values. So we're going to go ahead and we're going to make an x, y, table, and we're going to go ahead and start with 0. I always work backwards to find the -1 as well, so we can see what's happening on the other side of our y-intercept. And then we're going to go ahead and find out 1, 2, 3, 4. Now, we have pieces of information from our equation. The first thing that we have is we have our 0. It tells us here that our 0 is 10. So we know that we can go ahead and put a 10 in our 0. And then we know what our multiplier is. So we know that we're going to take that 10 and we're going to multiply it by 0.5 to have our next term. So let's go ahead and do that. We have our 10. We are going to multiply by 0.5, which is our multiplier to find our next term in our pattern. So times 0.5, and that gives us a 5. We're going to do that again. 5 times 0.5 using our handy dandy calculator, and we get 2.5. We're going to continue to do that times 0.5, and that's 1.25 times 0.5, and our fourth is going to be 0.625. Now we're also going to go ahead and work backwards to find that -1. The opposite of multiplying by 0.5 is dividing by 0.5. So I'm going to plug in my 10, and I'm going to divide by 0.5, and I see that that gives me a 20. Now that I have my table of values, I'm going to go ahead and simply graph those points on my coordinate grid. I have the point -1, 20. Go ahead and put that point there. I have the point 0, 10, which is my intercept. I have the point 1, 5, 2, 2.5, 3, 1.25, and 4.0625. So we're going to go ahead and take a look at this and make a smooth curve. Now, the thing is we haven't yet learned this yet, but exponential functions are going to have an asymptote. And an asymptote is a line that it will never cross. And we're going to end up seeing it with a plus or a minus at the end here. And that's going to be our asymptote. Because there's nothing there, it's +0. Basically, what that means is we're going to make a smooth curve, but it's never going to go below the x-axis. And we're going to have arrows on both sides. So go ahead at this point and make your smooth curve. But realize that it's going to continue getting closer and close to 0 there, but it's never going to go below that axis. So as you can see, we start big and then we get really, really small, really, really fast. And so this is called an exponential decay. And once again, we can see that right away because we can see that our decimal for our multiplier is a number between 0 and 1. So we know it's getting smaller each and every time. Okay, so that's what it looks like in an exponential decay. That's what it looks like in a table of values, and that's what our equation looks like. Remember that 10 is your 0, and your 0.5 is your multiplier, and we use that to form our table. Let's go ahead and take a look at an exponential growth pattern. So we have y is equal to 2 times 3 to the x power. And we're going to go ahead and do the same graph setup that we did here. So we're going to go -5, 5, -5 to 20. So let's go ahead and draw that. 1, 2, 3, 4, 5, 10, 15, 20, -5, and 5 and -5 on the x-axis. Okay. So now we're going to go ahead and we want to graph this exponential function. Now we're going to do that once again using an XY table. Once again, we always start with 0 because that's given information, but we want to work backwards and find what that -1 is as well so we can see what's happening on both sides. So we're going to go ahead and do 0, 1, 2, and 3 in this case. So we look up at our equation, and once again, the first number is our 0. And so we know that our 0 in this case is the number 2. We then go ahead and take a look at our multiplier, and we're going to go ahead and we are going to follow that rule to find what the next terms are. So we're going to go ahead and do 2 times 3, and so our first number is going to be 6. We're going to continue that. 6 times 3 is 18. Once again, use your calculator if you need to for these. And finally, 18 times 3 is 54. And as you can tell, it gets big so fast, that's going to already be off our table. Now, we need to work backwards in order to go ahead and find out what our -1 is, so we can see what's happening on the other side. So we're going to go ahead and do 2. The opposite of multiplying by 3 is dividing by 3. And we're going to go ahead and leave that as a fraction because we would have to round. It's not a terminating decimal. And so we're ready, now that we have our table, to go ahead and graph these points. We have the point -1 2/3. We have the point 0 2. We have the point 1 6. The point 2 18. Like I said, the last point is 54. Now I want you to picture, if this is 20, 40 is up here, 56 is basically going to be all the way up here off of your page. So that's how fast exponential functions grow. So we're going to make a smooth curve, knowing that our next one's going to literally be off of our page if we were to continue it. And once again, there's no plus or minus here, so we're going to have an asymptote of 0, which means it's never going to go below, once again, that axis. So we're going to go ahead and make a smooth curve, knowing once again it gets super fast, super big, and our next term for 2 here is going to be all the way up at 54. So this, ladies and gentlemen, is what exponential growth looks like. And we have exponential growth when we have a multiplier that is bigger than 1. So you should be able to look at an exponential function equation and picture what that's going to look like in your brain. Okay, ladies and gentlemen, let's go ahead and get to work and have some practice in our Desmos activity today.